write more.
Okay, welcome everyone to lecture 12 of 5828, Foundations of Software Engineering. I'm going to just pick right back up where we were, just do a quick review of what we covered last time, and then try to get through the slides that were assigned for Tuesday. We're going to be behind here a little bit in terms of what I had planned. Yes, question?
The lectures, can you do a couple of questions about homework and presentation?
Okay, yes.
First, I noticed you provided examples in the homework 3 of an example output, and I just happened to notice that it's all the producers, like the producer number, produced product, they're all collected, like there's never interrupted. 9 finishes all its production, and then 10 finishes all its production, and 3. Was that coincidence, like on how yours just maybe runs faster, or is that an intentional design?
No, that's just something that's an allowable, just a second. Note to GitHub, your default interface isn't helpful. I always want to go to this page, never to the other page. Okay. Yeah, so I have here nope, that's not it. In the repo that I released for homework 3, I have an example output here. And this was produced by a version of the program that I created and to fix and allow it to run all the way to the end. And to the end, the successful output is that it's printing, it prints out all of the product IDs that it saw. And you'll see that in the broken versions, you'll get gaps in the product IDs. There'll be a 0, and then the next one might be 10, then it might be 14, right? So you won't get a straight shot of all the product IDs 0 through 199. That's what you're gunning for at the very end once you've got it fixed. And I'm sorry, your name is
Tyler.
Tyler. Tyler's pointing out that in this output, there are places where the producers don't interleave. So a producer comes up and says producer 6.
If you do Control F, producer 6, and it highlights it, you'll see like all the highlights are clustered in one group.
Like this. Control F.
Yeah, when I Control F stuff, it highlights everything with it.
Oh, I see.
Producer.
Yep, so if we say producer 6, for instance.
And they're all collected.
Yeah.
They're all.
So in this case, in this run, producer 6 produced all of its products and without any other producers interleaving. So there was no producer 5 or producer 4 or producer 3 also in among those productions. And that's just an allowable behavior based on the way the code is written. So every producer is in a spin, in a loop, trying to get access to the lock so that it can go and update, make its products. Okay. And in this case, the scheduler chose to just keep giving it to producer 6.
So it's allowable to lock it out once one producer gets it?
Yeah, and this is the thing, is that there was no intention of locking. The producer 6 is in a loop where it goes, it says, can I have the lock? When it gets the lock, it produces one product, and then it lets the lock go. And there's nothing in the code that says that producer 6 should always get the lock. Right? So this just happened to be in this run. The scheduler is the one that chooses which producer gets the next lock.
Just coincidentally got chosen?
Just coincidentally got chosen. Yes, it just coincidentally got chosen.
Okay. There wasn't a preference.
There was no code in there that would keep them. Exactly.
Okay.
Yeah, and so here was a producer 1 produced product 76, and the next one was a producer, that's consumer 7, then producer 9.
Just like Control F producer 1, you'll see it's all clustered.
Okay, well, it just happened to be that way in that run.
Actually, all of them are that way, so I was...
Okay. Yeah, so that just is an interesting effect, but it wasn't in the code.
Okay, thank you. Yeah. And then also, are you going to go over more detail how to submit the presentation? Because I thought you said you were...
Yeah, I've got to create my apologies. I am falling behind on things. Grading is not on my radar currently. I won't be getting homework 2 graded anytime soon. I've got just this semester has been unbelievably crazy with respect to my major deadlines, papers, grant proposals. I have a promotion talk next week. So I'm behind on everything. But yes, I'm going to produce a Google Doc that you'll be able to say, my presentation is located here. And you'll be able to log in that way. Other questions on homework 3 while we're discussing it? All looks straightforward? Yes.
So suppose I create a GitHub repo, and my presentation is actually, I'm using Remark.js to create Markdown presentations. I can just put the link over there and say, okay, and then the GitHub repo link on the Google Doc.
Yeah. So the Google Doc I create will have a place where you put the URL of your repository, and then also a URL where you want people to go first for your presentation. Okay. So for people that do the Markdown approach, where it's just the Markdown pages are in a directory somewhere in your repository, you'll just point a link to the first page you want us to go to. If it's a website, so you have a GH Pages branch and you're posting a website, you'll have one link for the repo and one link for the website. Okay. But thanks for your questions. And actually, I'll go run it again tonight and see if I can get other interleavings. But yeah, just what happened that time. But I wasn't actually, the fix is not to make the producers
I noticed coincidence.
take in term. Yeah. So you want to make sure that, the original code, the broken code, you look at the producers themselves. This run line here says, while count less than 20, if q.size is less than 10, then create a product. And all of the producers are running this simultaneously. And so the fix is not to change this code fundamentally. It's just to add in some synchronization that'll happen, that'll make the threads not stomp on each other, but still produce. And so the code that I did was just one that identifies in this code a critical section and puts a lock around it. But all of the producers, otherwise the producers have the same code. They're all spinning in their loops trying to get access in through that lock. And for whatever reason, the scheduler decided to just let them turn take. And that happens sometimes. A scheduler's looking at a thread that's current, already running, and it'll just say, oh, you were already making progress. Let's have you keep making progress. And so you see that sometimes. Okay, but good question. All right, so let's just go back into Clojure a little bit, and we will get to speed. What this is going to lead us to is going to show us one example of parallelization of a simple sum, but also another version of that word count example that we were finishing up last time, but this time in Clojure. So just as a review, we've got in Clojure, you've got all your basic forms. These are kind of the primitive forms of the various values of the data types that they support. We reviewed Booleans all the way through keywords, and we noted that there was their primary data structures are lists, vectors, and sets, and maps. And something I haven't shown yet, which is called a record, but we don't have a strong need for the record just yet, so I'm not introducing it. We reviewed the syntax for functions. Those are lists in which the first symbol in the list has somewhere been defined as a function, either automatically by Clojure, like in this case with the plus operator. But I say plus operator, but that's really a carryover from other languages. Plus is just a function. Somewhere in Clojure's source code, it just says defined function, the name is plus, right? So it has no special status. Sort is also a predefined function by Clojure. So if you have a list data structure, which are these ones which have the parentheses around them, then if that first element's a function, it will try to call it, and everything else in the list will be a argument that's passed into that function. And the way you want to, the form you need to use to create your own functions is to use another function called defn. Actually, I think my guess is that this is something called a Clojure macro. Again, it's another advanced concept that we won't be discussing in lecture, at least not yet. But anyways, this is a defined function. You give it the function's name, its arguments in the range of a vector, and a set of forms. And then, as we mentioned last time, the last form in that list of forms, whatever its return value is the return value of the function as a whole. And then we briefly discussed the anonymous function syntax, and I can show this in context with the calls to map and reduce later on. But basically this is saying I don't want to go to the trouble of creating a name for this function. I just want to invoke it, define it, and have it be passed or invoked somewhere. So the anonymous function syntax that's a little bit more verbose is you just say fn, and then you give it the arguments, and then you give it the forms. And there could be one or more forms here to calculate whatever the function needs to do. But there is a special syntax here that will shorten that even further. So here you do not use the function fn. You do not define your parameters. You go straight to the body of the function. And basically, if you need to reference parameters, you reference them with percent signs. So if you just have a single percent sign in the body, that's telling Clojure that there's only going to be one argument coming into this anonymous function. If you start to do this, where you say %0, %1, %2, etc., then each one of those placeholders tells Clojure, oh, now it's a 2. Now we're expecting 2 arguments in, or 3 arguments, what have you. So this just references the arguments that will be passed into this anonymous function. And so this is, the quickest way to write a very simple function. Sometimes these anonymous functions, called lambdas in other languages, are very simple things. Add 2 things together, invoke this function, and return the result. And so this lets you get the expression of that to the bare minimum of syntax. We saw that we can create our own symbols by using the def, and this binds the symbol to a particular value. You can always rebind the symbol if you want. But we were starting to discuss last time that these values, once you create one of these values, like this 10 or this 3.14, those things are immutable. And so when you switch binding, if you say def pi equals this, and then you say def pi equals 3.1 or something like that, which wouldn't be a great value for pi, but it just rebinds the symbol to the new value. And here, if you do a function like where I take x, which is was defined as being 10, and add it and add 10, I get back 20, but that's just a value that was returned. X itself would still be 10. It doesn't change x in any way. So you can run this def command again. It's just rebinding the x. And yeah, so we discussed a couple of the control flow structures that we have. There's an if macro where it takes a function. That function needs to evaluate to true or false, or as in programming language context, we'll sometimes call about truthy and falsy. So you get your function might evaluate not to the Boolean value true or false, but it might evaluate to another value. And then I believe, if I remember correctly, in Clojure, if your function returns nil or false, it'll be considered false, and anything else that it might return is considered true. So almost everything in Clojure is truthy, which means it'll in a conditional context it'll evaluate to true. If you want to have it evaluate to false, you need to make sure either nil or false is returned. So then here it's a standard if statement. If this is true, then we are going to return the value of our first form. Otherwise, we return the value of our second form. If we have multiple conditions to evaluate, we can use the condition statement. And this will just check these predicates in order and then return the associated form. And then to do a default case or branch, you just need to put a symbol here, and this is actually ties into what I was just saying. There's nothing special about that colon else. It's just something that evaluates to true. So all of these things will be checked, and they could evaluate to false. Actually, this particular logic, one of these will always evaluate to true. But if there was a situation where input could make all of these 3 evaluate to false, the next thing it looks at is this first condition here. It just happens to be a keyword that happens to equal true in a conditional context, and it will just return whatever is the second thing next to it. All right, and then we started to go into loops. We have this loop keyword, or sorry, a loop macro, which takes in a set of bindings and expressions, and then is expected to be paired with somewhere in the expressions a call to recur, which allows us to jump back to the loop. And then the expressions that occur in the recur statement get rebound. They tell us how to rebind the symbols that were previously created in the original bindings. And I went through this last time, so I'm not going to go into it in great detail, but basically here we had loop with these bindings, result equals empty list, and x equals 5. We checked to see if the x that was passed in was 0, and if it is, we're done. We're going to pass back the result, which is going to be whatever the list is at that time. And then here's the recur statement that's going to jump back up to this loop. And then the conj statement is a way to append to a list, so it's appending the value of x. And then we're rebinding x to say your next value is going to be x minus 1, which is what the decrement statement is here. And then we noted the fact that a function name is by default also a loop point. So you don't need to say loop in a function. You can just use recur. And if you do a recur, that is a recursive call. That's why it's recur. Recursive call back to the function. And it rebinds the parameters to the new values and then executes the function again. So those are the ways that you do recursion. And that's the way you set up recursion in Clojure. But we then said, you know, most of the time you won't be writing these things. You'll be doing things where you operate on sequences. So like this iterate here calls this dec value multiple times. And then this here says take the first 5 of that sequence. And then once we have those first 5 values, which in this case would be 5, 4, 3, 2, 1, that into then puts it into the target collection. And so then we talked about map and reduce as being two of the most primary, they often call them data shapers. You have got one data structure, you need to transform it into a different data structure. Map will take the input data structure, and for every element that's in the input, it'll produce one element for the output, but it'll return you another array. Filter is like map, except that the function has to be a predicate, either true or false. And then what that means is that anything that was in the input array that returns true will appear in the output array. And so when you call filter, you are not guaranteed to have the same length array coming out as you have coming in. Whereas with map, you're guaranteed if you have an array of 5 elements, then it's going to apply the function to each element, and you'll get an array of the same length coming out of map. And then reduce takes a collection and a function, and that function is going to somehow transform the collection typically into a single value, like a scalar, like a string or a number. Like if we ask it to add up everything that's in the input array. It can, if it wants to, be through clever kind of manipulation of the function, produce another collection. But reduce is really all bets off. You're sending in the input array as input, and there's no guarantee that what comes out has much relationship to what went in. Yes?
I remember in Scala that we used to do collections and it could have different types in it. Mm-hmm. Is it the same thing in Clojure? Or does it all have to be one type?
Yeah, no, if it's, I believe they can be different types. You can easily create a sequence that has keywords and numbers and strings, etc. And then the function that you pass to map will have to just be checking to see what those things are to then do the appropriate thing. So my default guess is that it will allow it, but we can always test it. And that's the best thing to do in these cases. So let's say def test collection is going to be 5 ken colon Ruby. What's another number here? 3.14159. So let's see what happens. Okay, Java long cannot be, oh, right, sorry. That should have been a vector. It was trying to call the function 5, and that's not a function. All right, yeah, so it was able to create that collection, no problem. If we now reference that collection, it prints it out. So now if I were to do a map on this, the function I pass in can't just blindly be adding them or be manipulating them. It's got to be aware that it's getting a heterogeneous collection of values and then do the right thing. So then Clojure would have, I would assume it would have ways of saying, Are you a number? Are you a string? Are you a symbol? And then you'd have to have conditional code on that. Okay, so map and reduce will figure prominently as you move forward in your careers. If you step into jobs where you're going to be doing the analysis of large sets of data, map, reduce, and filter become primary things that you do, where you say, hey, load up this data set of 100 gigabytes worth of structured data, and now map it to be this, now map it to be this, now filter to look for just these things, now reduce to some average or some metric that we're interested in. So these things will become very important, and you should start. It is actually a challenge to figure out how to learn to manipulate data in this way. It's not the easiest way. If you're used to Java imperative programming, for instance, switching so that you do all your calculations via map, reduce, filter is a big shift. It's a new API, a new set of constructs, and a new way of solving problems. What's great about it is that it's been shown to scale to petabytes, exabytes of data. Right? So it's a very scalable API once you've learned it. All right, and so we were starting down this path of looking at the first example that the book covers, and it's one where we start with inspiration. If we were to get an array of numbers in Java, this is the type of code you would see prior to Java 8 for summing up those numbers. And it's very imperative, which imperative means I tell you what to do. So do this first, then this next, then this third. And so I say public int sum, and then I say I need an accumulator to keep track of the total. And so it starts at 0, then I loop through all the numbers, and I keep adding them to the accumulator, and then I return the accumulator. So we should all be familiar with this style of programming. What functional programming will do is to say, let's see if we can become more declarative. We know that in the background, map has to loop over the array, but let it worry about how it does that. It might do it through a recur statement. It might do it in any number of ways. And in fact, actually, if you want to be horrified, you can use the source command to give you the source code, the Clojure source code for any function that you've got loaded in your REPL. So map is loaded by default. And we're all conceptually map is sort of like this, right? You've got this array coming in, you have an initial value somewhere initialized, and then you loop through the array, and actually this would be, if I wanted to be doing the correct analogy here, this is really a reduce, right? So we got some numbers coming in, we're going to reduce it down to a total. So what's the source code for reduce in Clojure? So it's all of this. And I don't even want to know what that does. But what's funny is map is even more horrifying. It goes you have to scroll back to the top. Map has a lot of different cases. And basically map is taking a very simple thing, a conceptually very simple thing, which is apply this function to every element in this map, and then there's all sorts of corner cases that you care about that if you do things in a certain way will lead to greater performance. And so this source code here is stepping through all of those corner cases. Fortunately, we don't have to worry about this type of implementation. If someone's already figured all that out, and thankfully they did, we can just call map, and basically we're declaring, I want this array to be processed in this way. You go figure out how you want to do it. And as we'll see, Clojure has a way of saying, oh, and if you want, go ahead and do it in parallel by just changing the name from map to pmap. Okay, so here's one way of doing this in Clojure. It's a recursive sum. It takes advantage of calling recursive sum recursively. So obviously numbers comes in. We check to see if the vector that's coming in is empty. If it is, then its sum is 0. But if it isn't, its sum is the first number plus the sum of all the rest of the numbers. So this is where the code starts to become a little bit declarative. Once you've mastered looking at these parens, you can see that it kind of just reads with what it's doing. What's important to note here is that in the Java version, we have this mutable variable. So this accumulator is mutable. It has one value at one instant, and then we start to loop through it, and we change its value. And of course, as we saw with the race conditions in the previous lectures, if there were a bunch of threads coming in depending on the sum that was being calculated, or could get access to accumulators somehow, if we don't sync up correctly, then we could get munging on accumulators value. But here, what's nice about this recursive sum is that there's no mutable values ever anywhere in this code. Everything always stays immutable. So when we call recursive sum, this numbers is fixed. We never change the array in any way, shape, or form. We check to see if it's empty. If it is, we return 0. If it's not, we get the first element of the array, and then we get the rest of the array, but that's just pointing in, doing a slice on the array, not changing the array, and then calling recursive sum where it becomes the new array. And in each of those call stacks, it is mutable. So there's no mutable state here. There's no way to get a race condition with this code. It's just not possible. The other thing to say is that I forgot to say, in languages that do this recursive call, so here, when I have this recursive call to recursive sum, that is like recursion in imperative languages where we are creating a call stack, right? So we called recursive sum once, we're going to call it again, that's going to create a new stack frame, we call it again, new stack frame, etc. So with this call, if I were to give it an array of 10 million numbers, it would fail because it's going to blow out the stack. But if I were to re-implement it, and we do in just a moment, to use recur, then what happens there is you get what's called a tail recursion going on, in which rather than creating a stack frame, the runtime realizes that, oh, I can just call this function again with new values and just do some bookkeeping around it. But then I can it literally becomes like a loop in an imperative language. It's not going to be in any danger of blowing the stack. So if you re-implement the sum to use loop and recur, you can take a 10 million element array and sum it up, no problem. If it crashes, it won't be because you've blown the stack frames. It's because maybe you had integer overflow or something like that. Okay, so now what we do is we can say, it's great. We could, if we wanted to, implement recursive sum that way, but we don't need to because we already have the reduce function. So instead, what we can do is just pass the array in, and then we're going to pass this collection into reduce right here as numbers. So the numbers from here goes to here. We're going to tell reduce that our starting value is 0, and then we have to give it an anonymous function that tells it how to reduce this to the value that we seek. And all it's going to do here is this function takes two values, the accumulator, which we saw in the Java code, and our current element, x. And then all we're going to do is add the x to the accumulator. And so we've just declared how we process, how we combine elements in this array. We tell it start with the value 0, and then here's your array. And so then reduce takes care of summing up all the numbers for us. And of course, we don't need to create this function, this anonymous function, to add two numbers. We already have a function that does that. That's just the plus function. So the final version of using reduce is to just say the sum of this array of numbers is reduce plus numbers. Right? Does that make sense? And then what's nice about plus is that they also have implemented all sorts of corner cases. Plus will not crash if you give it no numbers. It'll do the right thing. If you give it only one number, it'll do the right thing, and then it can easily handle tons of arguments. Now what reduce does is it just calls plus with only two numbers, and then just totals up the sum. Okay, and then the reward is that once you've implemented this function in this way to create it in a single-threaded way, you can, if you want, swap out a single-threaded version with a parallel version just by changing, in this case, 2 lines. Clojure has a package called reducers, which implements lots of things that can go, lots of algorithms that can go concurrently. And here we're bringing the reducers package into our namespace and aliasing it with the letter R. So basically any code down below that says R is short for closure core reducers. We just don't want to type that all the time. And so then our parallel sum is just give us the array and do what's called an rfold. And the fold in this case is just an alias for reduce, but in this case kind of indicating that it's going to do this in parallel. The same function and the same numbers. So what it does in the background is it takes the collection that it's given and breaks it up into groups of 512 each, and then it performs the reduce calculation in parallel across all of the machine's cores. And it basically sets up a tree of dependencies between all these partitions where it makes decisions. I'll do these partitions first, then these will be the next ones, then these, and I'll just keep reducing down until I get a single value. And here you can see if I take our sum, our single-threaded sum, and pass it as an execution into the time routine just wraps the execution with a call to begin and a call to end in terms of time so that it can print out how many milliseconds it can go. And so once you've got your single-threaded version, switching over to the parallel gives us almost a 50% improvement. In this, of course, this is all in milliseconds right here, but still this is 50% smaller with just changing one function, saying I know it now works in single-threaded, so now I take my reduce, which was single-threaded, and switch it to the one that's parallel. Now, of course, you won't see much difference unless you're passing in really large arrays, so that you actually have enough time to partition the elements, reduce them all in parallel, and total up the sum, and have that overhead. All that's overhead. In terms of the single-threaded version, doesn't have to do any of that. And so for certain size collections, the single-threaded version will just beat it every time because it's not pausing to create the partitions and then make sure that it's reducing them correctly. All that's overhead. So you have to get up to, here in this case was 10 million elements before you started to see the reduce actually having an effect. On much smaller arrays, the single-threaded version is going to beat it every time because it just starts and gets done. But on very large arrays, suddenly the overhead of doing the parallel setup starts to pay off. And even though we're doing all that extra work, this is now 50% faster because it's been able to go out to all the cores. And I can just show that real quickly in real time here. So I went to the sum directory in the functional programming directory of the book's source code. I typed line REPL in that directory. And what that does is it makes available all of the functions that we just discussed in the source code of that project available to this REPL. And so here's our sum function that we saw, reduce plus numbers. That's the single-threaded version. And here's our parallel sum. So what I'm going to do is this REPL over here in this other window has those functions preloaded. I can just show it to you. Here's source parallel sum. So it knows that that's the source code for that. And here's the source code for sum, which is just our reduce plus numbers. So it has those loaded. So now let's just take these calls here, and we'll define our numbers to be a range of 10 million integers. And paste. Now note, that came back really, really quickly. And you'd think, oh, wow, didn't it have to allocate an array of 10 million elements? That was pretty fast. The answer is, and I'm about to go into it in the slides, is that no, it's not. This call to range 10 million actually creates what's called a lazy sequence. And that means that it just says, oh, I know that you eventually might want an array of 10 million numbers from 0 to 990, whatever it is. But I'm just going to take a note of that, and I'm not going to do any work until you ask for the numbers. And then once you ask for the numbers, okay, then I'll give them to you. So that's why that came back so quickly. And just to show you, I'll do numbers dash large. Another symbol here, and I'm just going to make this 10 times bigger. So that's 100 million. And it comes back just as fast because it didn't have to create anything. All right, so now let's do this line here, which is our time sum numbers. And we're going to say paste. So now it's got to do, okay, so yeah, that was 162 milliseconds. So in this case, it might be really hard to beat. Let's do parallel sum. And that was just slightly faster, 109 milliseconds. So now let's do the obvious, which is sum large. So this is 100 million. That takes some time. So that was the 1129. milliseconds single-threaded. And here's our parallel. Uh-oh. 3,000, so that was slower. Let's see if we can get it to, there's 1,000, so still just a little bit faster. 927, so as it, now, it's kind of got a value, this parallel sum thing has been cached. But not much faster here. Oh, it keeps getting a little bit faster each time. Well, anyway, this is where you can start to play with this. And none of this is rocket science, right? Because the operating system is doing things where it caches things and tries to make things faster. So the first time you try it, it'll be super slow. The next time you try it, it'll be faster. It's the operating system's kicking in. That's especially true if you do code over the file system. So if you hit a directory that hasn't been accessed in a while, it has to read all of that from disk. But the operating system is smart. It sticks all that disk content into memory. So then the next time you run the program, it's super fast because everything came from memory. And that's just the operating system doing that for you. So there's all sorts of things that will kick in to try to make things go faster the next time you run it. All right, okay, so now we've got just barely enough Clojure knowledge to try to recreate the word counts example from the previous lecture, which was that parsing, and actually I changed it. Last year I had to go to 39,000, but this one, I'm back up to 100K. So this book's second example returns the word counts example. It's this count all the words that are in the first 100,000 pages of the Wikipedia articles. So what I'm going to try to do is get us, and I've got enough time, I'll get us through all the building blocks that we need to recreate that somewhat complicated example in Java and re-implement it in Clojure. So the first thing that we need to know is just a little bit more introduction to maps. All I've told you so far is that maps exist, but I didn't show you how to use them. So the way that we do this is we say def counts, and then we give it this square bracket, open curly bracket notation, which is fortunately pretty universal to all languages that maps have these as literal symbols. There's only one language that I know of, but it'll remain nameless, Swift from Apple, that uses square brackets for this. But this is defining a simple map where we've got two keys, Apple and Orange, and their values are 2 and 1. So now if I want to, I can call get, and get is the function that will reach into a map and pull back out the value for the key. So the syntax of this is the get function, the map I'm operating on, the key I'm interested in, and then this one here is an optional value which says, if you don't find the key, here's the value I want you to return. So it's a default value. So, and it doesn't actually change the hash table. It won't actually stick Apple 0 in there. It's just if Apple's not found, it returns 0. But Apple is in this map, and so we'll get 2. But banana, you can see, is not in the map, and so we'll get back the default value, 0. Then if I want to create a new map or change it in some way, I use the associate function. So I associate with counts, banana, and 1. And that's going to return a new map. The old map is unchanged, which has the original keys plus the new key value pair there. And then here I can use associate to change old values. So here I say associate counts Apple 3. We get back the original map, but now Apple equals 3 as opposed to 2. And so associate returns a new map. The original map is immutable. If you've got something pointing at the old map, it can happily interact with that map for time memoriam as the new map is handed and rebound to some other symbol. All right, and if you really wanted to save the new map, you could, in one operation, do that by doing the change and then rebinding the symbol. And then the old map, in this case, is no longer being pointed at by any symbol, and it'll eventually be garbage collected.
I have a question.
Yes?
When you did, you did banana 1 and then went to Apple 3.
Mm-hmm.
Did you take the banana out when you did that?
Yes, because in each case, I haven't changed counts. Right? So in all of these calls here, counts is the same map. It's Apple 2, Orange 1. And so here I got the value 2. Here I associated banana with it, and it printed out a new map, not the original map. Right? So then when I call this next one, count still hasn't changed. So now I'm saying create apple 3, and here's a new map that's being printed out with 3 for apple, but the original map is still the same. So if we see this in, if we see this in a light table, let's see here, light table, and start a REPL, and then paste all this in. It's setting up its REPL real quick. Oh, it doesn't like these string characters, I tell you. It's always something. So def counts. Actually, let me just see if I can do this faster by putting it first. VB edit. Paste a cut. Paste. Nope, still not happy. I don't know why. Is it unhappy with that? Nope. So yeah, so there's that value, and I can click on this to see the whole map. So now let's go to VB edit again, paste. Let's do this one at a time. What's the problem here? Unable to resolve symbol. Oh yeah, I don't want the output in there. Okay, so then here it's showing that it's calling apple and getting the value 2 from it. Now I see what I was doing wrong. I was showing the REPL output before. I don't need that here in this context, so there it's returning 0. And now let's associate counts banana. That. And so what we have is the original map hasn't changed, right? But here we've got a new, this thing creates a new map now that has banana in there. If I want it, I have to do a def again. I have to say def new map, like this. Right? And now down here I can say new map, which is that map, and then counts, right, is still unchanged. Right? So this is what you have to get used to in these functional languages, is that values once created never change. Right? So I can't say like x plus equals, I can't do x plus plus in these types of languages. X plus plus says, oh, your value is 5 and now it's 6. And you've gone into memory and you've changed the old memory location to now have 6 in it. And that, according to functional programmers, is evil. Don't do that. Right? And the reason why it's evil is race conditions. Right? If we change, we have multiple threads coming in at this one single memory location, and one of them changes it, and not in a synchronized way, then everyone else reads the old value. And in fact, that's what you see when you run the homework 3 problem for the first time. It all comes up, and all 9 or 10 producers say, I created product 0. Right? They all got in and created the first product. And there's a mutable variable inside of product, which starts out as 0. They all read it before any of them increment it. And so the first problem that happens in homework 3 is that 10 product 0s are created. And then someone tries to create product 11. And so all sorts of interesting things go on because that variable is unprotected. In a language like this, that could never happen, because whenever I create a value, it doesn't change. There's no way to have, and with the things we'll see coming up for Clojure, there are ways to make sure that if it's 0, then I'll read 0. But if someone else has changed it, I'll read 1. Right? There won't be any way for an out of order update to occur. So that's what we're leading up to, is this way of doing concurrency without having to worry about data changing out from underneath us. All right, so clear on maps so far? I apologize, it does get more complicated as we move on. So here we go. What we're going to do is use maps to, just like we did in Java, use a map to keep track of the counts of how many words we've seen. And so we got a function here that's called, this is one way to implement this, called word frequencies. So imagine we've parsed a page from the XML document, and we have all of its words in a sequence, a list. We're going to pass that list to word frequencies. And actually down here at the very last line, that's not true. Turns out that Clojure already has a function that does this called frequencies. So we'll use frequencies moving on. But here's an implementation of it. We've got this list of words that we just read from the document. We pass it into word frequencies. It's going to do a reduce. It's going to take the collection for reduce as the last argument. That's down here. So there's words being passed into it. Reduce can take an initial value, and so the initial value that we pass in is an empty map. Okay, so that's a literal say, here's our empty map. Our reduce function is this next line, this second line here, which I skipped over real quickly. And here's what it does. It's going to take in a map called counts. It's going to take in a new word. Okay? It's going to call, or we jump over here, it's going to call get on the map, passing in the word as a key. And it's going to say, do you have this word? If you do, give me its value back. If you don't have this word, the default value is 0. Okay? So now we're going to get back either the count or 0. And then the next parentheses out increments that value. So 0 goes to 1, the value goes to value plus 1. And now we have an association, a call to associate. So associate with this word in the counts map the new value. Okay, so it looks it looks really daunting, and then when you get down to it, it's like, oh, that's all it's doing? So call the map, get the current value. If we don't have it, it's 0. Add 1 to it with increment, and then put that into the map as the new value. Now remember, two things going on here. One is associate returns a new map, right? The old map hasn't changed. But what reduce does is it's taking the new map, and it's going to be it's looking for the combination of the previous map and the new map, and it'll figure out that this function here is the one that's telling it what the new value is. And so every time it calls it on the next word, it pulls back, it gets a map, and it rebinds and uses that as the current value and then calls the next one. Right? So that's what's going on there. And so in this way, you take this whole list of words, what comes out is a map of all the words plus the number of times we saw those words. Does that make sense? So if we had, and we can do this real quick. Oh, that's going to kill me. I got to come out of hit escape each time. Okay. So let's go to, I don't know, let's try light table here. Maybe I could do the REPL, but let's try this first. All right, so let's make sure that it's formatted here so it looks nice. Actually, in this case, we have enough space, so there's the whole.
Professor, can you please
Yes.
zoom in?
Yes, let me see if it will take a zoom here. All right. Now let's see if should have this now something we can call. So if we say word frequencies, and we need to pass in an array, a vector of words. So let's do can, and we'll do Mario, Sahar, and Mazen. Then we go like that, and this. So here's what we get back. Is a map that says we saw Mazen once, Sahar once, Mario once, Ken 3 times. Right? So what this did was it took this array, Ken, Mario, Sahar, Mazen, and it went up into word frequencies, and it asked the counts array, it asked the counts map, do you have the word Ken in it? Now here's our initial map, right here, being passed in as the initial value. So the first time we said, do you have Ken in it? It said, nope, don't know Ken. So I get back 0. The increment function gives me back a 1. And then I'm saying, create a new map that has Ken with the value 1. And then we go ahead and do this again for Ken. The next time it would be 1 to 2, and then 2 to 3. And then everyone else was just a one-off, so 0 to 1, 0 to 1, 0 to 1. And what we get back is this map. All done immutably. Yes, Alex?
Was the order of the return values, so it counted Mazen first, then Sahar, then Mario, then Ken. Can that change, or
Oh, yes.
How do you choose the order of the return?
In most languages, maps do not guarantee an order when you print them. So you say, hey, give me your keys, and it'll print out the keys. The reason why is that maps underneath are often implemented as sets. And so you're just putting the key into the set, and sets themselves are not ordered. And so you can say, hey, set, give me what are your values, and give back one ordering, and then immediately say, hey, set, give me your values, and it'll give you back another ordering. So don't depend on ordering of keys in maps and sets unless, like in Java, you create a tree set. A tree set is one which uses a binary tree underneath the covers to maintain an order for the keys. So if you just do a regular old, in Java, hash map or hash set, you're going to get unordered behavior with respect to printing things out like this. Okay, so that's the first step. That's, if you think about it, in this thing, we have 100,000 pages. We want to know how many times all the words appear in those pages. That's like the primitive thing. You need to have this function first, right? Now, we won't see this code again because it turns out Clojure has something that does it called frequencies. So this is just the built-in version of this routine. If I paste it down here, and then just turn this to frequencies, we'll still get the same value. Frequencies is just Clojure's built-in operation for this. But they wanted to show you the code first. Okay, so now, there's so much new stuff to cover. So Clojure has a concept known as partially applied function. And this is where functional programming, when you first come to it from being an imperative programmer, and this is one of the first hard concepts to get. And it's, in other contexts, it's called currying. And they won't even talk about partially applied functions, which in my opinion, is easier understanding. They'll just use currying because someone named so-and-so Curry invented it. So the technique itself is called currying after that person, but it doesn't help you understand what it's doing. But basically, it's this. You got a function. The function takes 4 parameters. What you can do is you can say, hey, I have 3 of those parameters. I don't have all 4 right now. So what I'm going to do is call you with the 3 that I have. And what you're going to give me back is a function that needs just that last parameter. And then once I call that last parameter, we'll call the original function. So that's what partially applied functions do. So if you imagine this, and I'll ask you this, I'll show you an example in just a minute. But if you imagine let's say we've got a function that needs to print out a first and last name. So the original function just says, print, and it's got an argument for first and an argument for last. So you know this one friend, but you don't know their last name. You just call them Bill, right? So that's their first name. So what you do is you call this function in the partially applied thing, saying, I know the first name is Bill. So give me a function that knows that the first name equals Bill. And so then you can think of that function that's coming back as Bill, what's his last name, right? And then we need the last parameter. We need to ask Bill, what is your last name? And then we can finally supply that. And then what we're going to supply that to is not the original function, but to this new function that came back. So we pass in his last name finally. Let's say it's Anderson. It will then finally call the original function with Bill and Anderson. Yes?
Does it evaluate part of the initial function first, and have it a partially evaluated function, or is it?
No, it's basically suspending execution. It's basically saying, oh, you only have 3 of the parameters, but you need 4. Here's a function that only needs 1 parameter, and I've remembered the 3 you gave me. Yeah. Okay, so here's an example of that. Let's create a function that's called add5. And so the way we create partially applied functions is with the macro partial. And we tell it what function we're going to be partially applying. And then we give it the arguments that we want it to know. Now remember, plus is one of those super crazy functions that can take 0, 1, or multiple parameters. But in this case, partial will figure out that, sum is saying, okay, I'm being called with 1 number. And that number is hardwired to be 5 for this function, add5. Now I can give add5 any set of numbers, 0 more, 1 more, 1,000,000 more. And it will act like plus, but the first value will always be 5. Right? So now I've created a new function which 5 has been hardwired in as plus's first argument. So now if I say add 5 by itself, plus is being called but with just the number 5, so it just returns 5 plus 0. If I add in 10, if I pass in 10, it will take 5 plus 10. And if I add in 4 tens, I get 45, right? Because the 5 is just hardwired in. The add 5 function is remembering, oh, I was called with a 5. I got to pass that into plus first, and then whatever else they give me. Okay? So that's the basic idea of partially applied functions. When for me, when I first came into this and started learning this, I called it mind bending. It's like, okay, you're attacking things I hold sacred. But you eventually get to view it as being fairly normal and actually quite useful. So here we can apply partial to anything. So here I have a function that I'm calling add 5 to everything. And the call this time that I'm doing partial to is map. Right? And map is one of those functions that takes a function, another function, plus an array. And so what I'm doing is, hey, that partially applied function I called add 5, that's going to be my function for map. Right now, I get back this function add 5 to everything. Map already has its function, which is add 5. It just needs the collection. So this add 5 to everything is expecting just one parameter, which is the collection. And so when I pass in a collection to add 5 to everything, it calls map, in which it's going to add 5 to all the numbers that it was given. And so it takes 10, 20, 30, 40, et cetera, to 15, 25, 35, et cetera. What's cool here is this is a partially applied function that we pass to another function that's now partially applied. And so add 5 is still waiting for its argument, which finally comes when we do the map, and it passes in the element. So you're building on functions on tops of functions on tops of functions. Okay, so we need to understand, I need to introduce you to 4 more concepts with Clojure, and then we can actually show you the word count application. So resequence takes a regular expression and a string, and then produces a lazy sequence of all matches of that regular expression. I'm just going to assume you know regular expressions. If you don't, they're pretty easy to grok, and there's tons of tutorials online. But basically, it's a way of saying, here's a pattern. Tell me if the pattern is present in this string. And a regular expression matcher will either say, yep, the pattern appears right here, or it doesn't appear. And what this will do is, if the pattern appears multiple times, we get a sequence of all the matches out of reseq. And we'll see what this means in just a minute. Now, mapcat is referred to in other languages. If you have experience with Scala or other functional languages, mapcat is Clojure's flat map. So what mapcat does is you get a sequence, and each element of the sequence is another sequence. So in Java land, you can think of this as arrays of arrays. So you get one array, and every element in the array is another array. Okay? So then what flatmap or mapcat does is it produces a single sequence in which all of those other sequences have been, everything's been pulled out of their sequence. So if you had an array of arrays, let's say it's just really simple, the first element is an array of 2 numbers, and the next element is an array of 3 numbers. What you get back is one array with 5 numbers. It's pulled all of the values out of the sequences and stuck it into just one big sequence. Yes?
Does it simply concatenate? I'm assuming it does. Or
Yes, it just concatenates as far as I know. So here's our example. Def first will just be an array of 2 numbers. Oh, that's right. Don't want to do that. I think I just renamed a core function. Let me just start over real quick. First is the function that says if you have a sequence or a list, give me the first element, and I just made it an array. That's not good. At least it warned me. So let's say first element is going to be 1 and 2. And then we're going to say second element is going to be 2, 3, 5. That. Now I want my sequence of sequences, so I'll call this just elements. And that's just going to be a vector containing first element and second element. And by the way, the Clojure REPL has tab completion, which I recommend. Okay, so if I look at elements now, I get back a vector which has two vectors as things. So then mapcat of elements, right, returns a lazy sequence. So I need to say into a new array like this. We saw into on a previous slide. Oh, come on. This is where my Clojure knowledge is not sufficient to do this. Let me just do a take on it here. So we know it has 5 elements. Let's try take 5. Oh, come on. I sequence from Clojure. Sequence from... Darn it. All right, well, if I see what happens, maybe, does it know mapcat? Yes, it does mapcat. Returns the result of applying concat to the result of applying map to F and collections. So it actually needs a, okay, all right, well, I wanted to show it to you, but I can't, at least not in line. There's going to be a mapcat example coming up, so we'll see if I'm just calling it wrong in a future slide here. All right, so merge with is another function that you just need to be aware of. Merge with takes a bunch of maps, and it takes a function that, if given 2 maps, creates 1 map, and then merge with will create the union of all those maps using the function. And so in our particular case, we're going to have multiple threads creating multiple maps count with word counts, and so we just need to merge them so that it has the global count across the threads. And then finally, lazy sequences. I talked just a little bit about it already. We'll go into just in a little bit more detail. But basically, Clojure can generate a sequence that might have an infinite number of values. And it does that by not trying to pull it into memory. It just knows how to create the sequence on demand. And then we'll work with that. We'll generate numbers as things ask for them. So let's continue on. All right, so resequence is pretty simple to understand. You give it a sequence and a pattern. It looks for matches of the pattern and produces a new sequence that contains each match. So here, if I say get numbers, passing in a string in this case, and then I say resequence, and then here's a regular expression. \D stands for digit, plus means 1 or more digits. So this pattern is look in the string for instances of 1 or more digits. So here, if I pass in get numbers 1, 2, 3 Boulder Ave, 256 Dash Drive, 5678 Pyramid Lane, this pattern \D plus will find 1, 2, 3, 256, 5678. These are all sequences of 1 or more digits. And so what comes back is a sequence, a list, with those numbers in it. Okay, and so what resequence is going to do for us is we read in from the XML document the whole content of the page, and we're going to just tell it, break this up into words. And we're going to give it a regular expression that looks for things that are not white space. And so rather than looking for white space, you look for not white space and return back a sequence of all the words. Okay, mapcat, maybe this will give me an example here. Oh, right, I see. I've got to do it inside of the, okay. So mapcat is you perform a map operation that produces a sequence of sequences. So here's map get numbers, and we're looking for numbers inside of this. So we just saw get numbers on the previous slide. So here's a sequence, and then get numbers goes and returns a sequence of all the numbers that it found. And so this is going to return this, the sequence here of multiple numbers. And so then what you need to do is you want to have all those things be just in a single sequence. So rather than here's an array or a list of 1, 2, 3, and 4, 5, 6, and here's this array and here's that array, what we want is one array that has everything in it. And so you can, if you want, do this in 2 steps. You call map first to get all the sequences, and then you call flatten, and it will flatten all the subsequences and give you one sequence with all of the elements in it. But you can do all of that in one step, mapcat, by giving it the function and the original input, and what comes out is an already flattened sequence. So what I was doing wrong in the REPL over there was I was just handing it a sequence, and it was waiting for a function. It needed a function. And then it was just going to act like map, but do the flattened part for us automatically. So if I have time, I'll go back and show you a way to make that work then. Okay, so merge with does just what I said. You give it two maps, and then you give it a function, and it will create a new map. So here we've got maps with symbols Ken, Max, Miles, Lilia, and Miles. And you say combine these two, and when you have to combine two duplicate entries, use plus to do the combination. So here, Ken appears in both maps, so the new map has Ken with 50. And Miles had a 40 and a 10, so he shows up with 50 as well, and so on. Now, we're just using plus because the values of this map have integers as their values, but this is a generic function. You can pass in maps that have all sorts of complexity, all sorts of different types of values. You just have to give it the function that knows when I have two of the same keys, what do I do to combine them? And you get back a single map combined. All right, and then finally we have our lazy sequences. So here's this example of making one of these lazy sequences not lazy. So in the REPL, if I say range 1000, it's got to print it out. So it's actually got to create the range and then print it out. So now we can test our REPL's limits here by just increasing this by an order of magnitude each time. Had to think about that one, and it's going to take a while to print this one out. So I won't do it again, but eventually this will crash, right? Because it's going to have to keep trying to bring this into memory. But it's only doing this because the REPL said, hey, I got to print it out. And so then it created it. What it actually does when you use it in programs is say, okay, you want 10 million, an array of 10 million numbers. I'll remember that. And I'll remember how to create that sequence, but I'm not going to create it right now. So instead, yeah, that was dumb. Almost done. There we go. Instead, you can do things like this. Take range that. So that's really big range. We do not want to create that one. But here I tell it, I just want the first 5 elements. So boom, right? It didn't create all those numbers. It just started to create the sequence on demand. It knew it needed the first 5, so it gave me just the first 5. So sequences that act like this are lazy sequences. Okay? What's interesting about lazy sequences is that they retain their lazy nature across multiple function calls. So what's really interesting here is that this range right here, I don't need the 0, I can just give it the upper bound as we saw. This creates a big lazy sequence of 10 million or 100 million numbers. Then I'm creating a map call, and I pass in this case, partial, so I'm going to be multiplying 2 to every number. And I call map. Well, what's interesting is map returns a lazy sequence. Right? So if I just say def lots of numbers times 2 and pass this into it, nothing happens. It just says, okay, I'll take a note of that. Right? And it doesn't actually do any calculation until I tell it, in this case like here, take 10. And now finally, if I do take 10 on lots of numbers, as we just saw, it'll print out the first 10 of those. But if I take 10 of lots of numbers times 2, it knows that first it has to get the elements from the range, then it has to multiply 2 to each of the ones that it generated, and then pass that back. But it only does the minimal amount of work that we ask it to do. Now, all bets are off if I were to say, evaluate that at the REPL so that it has to print it out, or if I have to say, take all of those numbers and put them into this other collection, because now I'm saying you have to create them because we have to put them somewhere. Anytime I do that, then it will trigger potentially a infinite loop. Like you can create, there are ways to create infinite loops where you just say, repeatedly call increment. And so if increment is called without a value, it's 0, then 1, then 2, then 3. And if you put it in the context of repeatedly, it's just going to keep calling it. until it ends. Well, it's never going to end. It's just going to go off to infinity. So these things are efficient and fast. Okay. So you can even get to the end of a list without too much memory strain. If you say lots of numbers times 2, and then tell it drop the first 9 million elements, and then take the next 10, it does have to calculate those 90 elements, but it does it in a loop. It doesn't do it in a stack frame. It does it in a loop. So it'll take a little bit to burn through all of those numbers, and then it'll give you the 10 that you asked for. So it's pretty without much memory strain, it does get to the end of the list and give you the ones that you want. So if your JVM has a nice amount of memory, this operation is fast too, and I ran it on my machine last year, and that's what it produced. You just have to avoid asking for the entire sequence. If you ask for the entire sequence, it'll create it, and then it's up to your JVM to have enough memory to actually bring it all into memory so that it can do it. Okay, so now we're ready for the new word count program. And what we have here is 3 source files. Do not look into pages.clj. You'll run screaming. I know I did. As I say here, it has functional XML parsing code that will make you lie in bed awake, unable to sleep at night. It's really, really crazy. Don't even look at it. But that is the code that's reading the XML file. And then core.clj, words is the function that says once I have a page from the XML file, I need a sequence of words. And so that we're just using the resequence function that takes a regular expression and then gives me the lazy sequence of matches. Okay, and this \w, I think, stands for word character. So this is saying one or more word characters. So it'll go for words. As soon as it sees white space, it stops, and we'll skip past the white spacing and then get the next word. So that means the rest of the code that we have to understand is in the core.clj file, and we can look at things. So what's nice about the functional language here is that here's the whole word program in a single-threaded version. So to count the words, I need a set of pages. For those pages, I need to call getWords on each page. That's going to give me back sequences of words. So mapcat those so that we get just one big long sequence of words. And then call frequencies, which we saw earlier, which would count up the number of times we saw each word. And there it is. That's the whole program. If you go back to the Java program, it was 3 or 4 files, tens of lines each, right? And with this, getWords was a function we defined. We had to go define that right here. Right? Well, I'm not showing you the XML parsing code. Trust me. So this does everything. Once the pages have been brought into memory, this does everything we need. So now I think I might have talked about the average. Yeah. So here, with the sequential version, what you can do is you can say, my pages are going to be take the first 100,000 pages, calling get pages on the big XML file from Wikipedia, and then call call in pages to count words sequential. And then here I actually have to include a call to count because this is a call to frequencies. And if I remember right, mapcat, getWords returns lazy sequences, mapcat returns a lazy sequence, and frequencies, I know frequencies turns into a map, so I'm not sure. But if you ever define a whole program in which everything defines a lazy sequence into a lazy sequence into a lazy sequence, the first time you run it, nothing happens. Because it's just like, I take a note of that, I take a note of that, I take a note of that, done. You didn't tell me you wanted anything from the sequence. So oftentimes you'll see there'll be like one little thing you do that then tells Clojure, nope, go calculate everything. I need the answer. So this one took 4.2 minutes to do 100,000 pages. The CPU utilization sat right at about 100%. So then what the book does, and I'm almost out of time, so I'll skip over this without going into too much detail, but basically what it does is, now that we've got those kind of underlying understanding of what's going on, here was the first way it tried to do this parallelization. So it's going to do a reduce, and that reduce is going to be on a set of maps that are being created, in parallel by pmap. Now pmap is just the map function, but it tries to do it in parallel. And it does it the same way reducers does. It takes the input collection, in this case our pages, which was passed into us, and divides them up into partitions of 512 pages each, and then tries to do its function, which in this case is create a list of maps. So create a map that counts all the words. So here's what's happening. Sequence of pages. The function that's going to be called is getWords on the page. So we get back a map of all the words in that particular page. But this was a map on all of the pages. So what we get back is one map per page, right? And so that's what pmap will do for us, is count all the words individually on all the pages at once. And then the partial merge with plus says, now take all of those individual maps and add them all together into a single map that has all the counts. And that final stage of reduce, in this case, is done as a single-threaded version. And you get 50% faster, 2.42 minutes, about 300%. Which means this pmap was able to achieve some concurrency and count words in parallel. The problem is that partial merge with, this all turns into a lazy sequence, because this reduce returns a lazy sequence and the pmap returns a lazy sequence. And so what happens when we finally say, hey, tell us how many words there are in a function I'm not showing, the lazy sequences kick in and they start to do things kind of sequentially. They'll get the first page, pass it to getWords, merge with, get the next page, pass it to getWords, merge with, get the next page. And there was a little bit of concurrence that could go on there, but you were getting basically contention around the final global map of having to merge in each individual map into the final map. And so that was very similar to what we got to on the Java version, where we had a version where we were trying to merge in the counts, and we were getting contention around that data structure. This is happening again in the Clojure version, but it's because of the behavior of lazy sequences. The lazy sequences are causing some of it to become sequentialized as opposed to performing it in parallel. So the final version of making it parallel changes it so that what we do is we call partition all on the pages coming in and force the pages sequence to be realized. And as soon as we've done that, we actually get in memory multiple partitions all at once. And now we can do pmap in parallel on those partitions, and you get way more concurrency, about 500 to 1,000% CPU is what I saw. And it's 1.2 minutes, which is 50% faster than the previous parallel attempt and 71% faster than the single-threaded version. Okay, so that was a huge amount of stuff to take in. What I'm going to be doing is, after this current assignment, once it's done, I'm going to be adding one more assignment that's going to have you work with Clojure and do nothing this complex, but get to the point where you implement something sequentially and then switch it over to something that's in parallel, just to give you a chance to work through all of this. Now, one of the things I'm going to do on the D2L website is I'm going to create a page on the forum that says, hey, I'd like to work on this next assignment with other people. So you can form teams if you're not already in a permanent team for the rest of the semester. People that want to just get together and learn Clojure together, basically. I'll provide that as well, or maybe I'll just do it as a Google Doc as well. So if you want to pair up and learn Clojure with other people, you can do it that way. All right, so I will see you next week. I'll be posting stuff to the website this weekend with the schedule for next week. There'll be 4 lectures next week. 2 regular ones and 2 extra ones.